Dear students, in this video lecture, we are going to learn about the slope deflection method. It is one of the methods to analyze the indeterminate beams. So we are going to study some more methods like moment distribution, stiffness method and flexibility method in matrix analysis. So it is a simple method. Slope deflection method is simple method, very easy for calculation, but it is less time consuming method compared to the moment distribution method. So we can start this video lecture. The displacement method consists of slope deflection and the moment distribution. Both are displacement methods. Even the stiffness matrix method is also a kind of displacement method where the displacements are to be calculated. The flexibility method, matrix flexibility method is a force method where the forces are to be calculated. The forces are the unknowns. So here the displacement method is the slope deflection method where the displacements and the rotations are the calculations. One thing I want to make clear that when a beam is subjected to a particular loading, it is a point load, it will deflect. So we will have some rotation theta and some deflection here, and at a particular section we will have the shear force and bending moment. So the equations of slope deflection equation consisting of theta and delta to calculate the moment at particular span or in between the sections. So if the theta and delta is included in any problem, then it is clear that we are going to calculate theta or delta. So what are the parameters related to this in a force coordinate? If you apply a force, there will be a response of delta. If you apply a moment, there will be a response of rotation. So you should very clear about this. If you apply a force, there will be a deflection. If you apply a moment, there will be a rotation. So now coming to this equation. So this moment equation consists of delta and theta. That's why it is called a displacement method. So the moment distribution method as well as slope deflection method as well as stiffness method are the methods of displacement methods. Force methods are flexibility method and some integration techniques also coming under force method. So now the overview of slope deflection method includes the study of degrees of freedom as well as kinematic indeterminacy. Why we are going to learn about the basics of analysis, that is degrees of freedom and kinematic indeterminacy? I am going to clear this point. So we are going to calculate theta and delta. We are going to calculate theta and delta. So in basic, the static indeterminacy is the number of unknowns minus number of available equations. Simply we can say like this. So in that we are counting the reactions RA and RB. So two number of unknowns, two number of equations in case of beams. So I is 0, indeterminacy is 0. So the static indeterminacy comprising the calculation of reactions and moments. The kinematic indeterminacy is the calculation of number of degrees of freedom. Kinematic means the movement. So which are the characteristics allowed in a structure is called degrees of freedom. So in this point the theta is allowed. So some theta can be measured, but delta is not allowed. So the theta and delta are the characteristics to count the degrees of freedom, and RA, RB are the characteristics to count the static indeterminacy. So degrees of freedom is connected with the kinematic indeterminacy. The reactions and unknown moments are connected with the static indeterminacy. Static indeterminacy means reactions, unknowns, moments. Kinematic inertia means number of rotations and deflections. You should clear about this point, then we can continue to this methodology. So the displacement and rotations are the unknowns here. The equilibrium equations for each node in terms of deflections and rotations should be made. Some equation to be made in slope deflection method for each span of the beam in terms of deflection and rotations at each node. So we have to solve for this equation by keeping some equilibrium as well as compatibility conditions. So for example, if you take this structure, we have some moment AB, which is denoted as M suffix AB. Here M suffix BA, from B to A it is denoted as MBA, from A to B the moment is denoted as MAB, and theta A is the rotation at A, theta A, and theta B is the rotation at B, and delta, in any case if the support sinks for a delta amount, then delta will come into the picture. Normally delta will not available in all the problems. In some case the support sinking problem is given, then delta will come into this picture. So connecting all these theta and deflection, here it is theta B. The deflection moment, we can write the moment distribution, slope deflection equation equal to M bar AB, which is the fixed end moment, 2 EI by L, 2 theta A plus theta B minus 3 del by L, minus 3 del by L. So this is the equation can be written from A to B. Similarly, we can write this equation MBA bar plus 2 EI by L into 2 theta B, where the B comes first. Here also we should mention 2 times of theta B plus theta A minus 3 del by L. So the delta will not always come into the picture. Whenever the support sinking problem is given, then only we have to consider delta value. Otherwise, we can simplify this equation with theta and moment. MAB bar and MBA bar are the fixed end moments. Fixed end moments, which is considered to be a fixed ends for a particular span. So some particular loadings, we can easily memorize the M bar AB formula for different cases of loadings. The applications of slope deflection equations can be extend to the continuous beams, frames without side sway and frames with side sway. Continuous beams we already know. It is like 2 span or 3 span continuous beam. If the number of span increases, then the difficulty of the problem increases. The frames with side sway means it is a portal frame with the different support conditions. When a horizontal load is acting from left to right, this frame is considered to be the frames with the side sway. If there is no horizontal force, the frame is symmetrical with the given loading and also the support condition, then this frame is considered to be the frames without side sway. There are different loading positions and support conditions which make sway to the frame. So here we can discuss the different steps. The following steps are involved in the analysis of continuous beams by slope deflection method. Each span of the continuous beam is taken as fixed beam and the fixed end moments are noted. For example, if you given with the problem like this, consider each span A to B and B to C separately. Consider the fixity and the ends, and you consider the loading given in each span. First of all, for AB I am considering a point load W. For BC, I am considering an UDL, and UDL of, for example, you take W Newton per meter. So for a fixed beam with W point load, the fixed end moment is WL by 8. For a fixed beam with an UDL, the bending moment, fixed end moment at the ends are having the direction of the mentioned direction from this direction to this direction. So this is the sign convention or the direction of fixed end moment. You should clearly note down this moment. So for a UDL with a span, to find the fixed end moment, it is WL square by 12. So it is given in this point. The first two values for the beams with varying distances. If you take AB distances at a point load W at a particular point, then the fixed end moment direction is like this. If you consider the direction, it is anti-clockwise, so it is negative, and it is clockwise, so it is positive. Direct in sign convention, the anti-clockwise is negative and the clockwise is positive. And the moment from A to B, MAB bar is equal to WAB square by L square minus. Next, MBA bar equal to WBA square by L square. So you have to memorize these formulas, WL by 8 and WL square by 12, WAB square by L square and WBA square by L square. So the first step is to consider each span as a fixed span and calculate the fixed end moment for a given type of loading. Either point load at the mid span, which is WL by 8, and UDL throughout the span, WL square by 8. So it is symmetrical, no. So both the ends we have WL by 8, WL by 8. Here WL square by 12 and WL square by 12. For a point load with a varying span, it is WAB square by L square. Here from right to left end, it is WB square by L square. So you have to memorize this formula for calculating the fixed support moment. Next, use the slope deflection equation, which already I have written. That is, if you form MAB equation, so MAB bar plus 2EI by L into 2 theta A plus theta B minus 3 del by L. Similarly, you can write for MBA. So you have to write this slope deflection equation for each and every span, and you can include M bar AB as WL by 8 or WL square by 12 or WAB square by L square. It depends upon the given the loading condition. So you can write with this fixed end moment and continuing slope and deflection terms. So if the problem is not a support sinking problem, you can eliminate 3 del by L in initial step itself. If the problem is a support sinking problem, if there is a delta value given in the problem, you have to consider this term. So the next step is to write the slope deflection equations. Next, joint equilibrium equation. What is meant by joint equilibrium equations? You consider this joint. Actually, here the moment at the simply supported beam is 0. The moment at simply supported point C is 0. Already known concept. The moment will exist only in the fixed end. The moment is 0 in a simply supported end. So by using this concept, we can know MAB should be 0 in a final result value, and MCB should be 0 in any problem. A simply supported point having no moment of resistance. There is no resistance for the moment. It will rotate. A simply supported point will rotate. That is the direct meaning. So there will not any moment of resistance. So MAB should be 0 in final answer and MCB should be 0. What about the midpoint? The midpoint will have, originally it is a simply supported point. So the resultant moment after any calculation should be equal to 0 at point B. How we can write the moment equilibrium equation? Sum of moment of the span MBA plus sum of moment of the span MBC equal to 0. So this is the equilibrium condition or moment equilibrium condition which is used to solve this problem. So the next step is to write the joint equilibrium equation. Solve the joint equilibrium equation to get the unknown reactions. First of all, you are writing number of slope deflection equations from the given problem. How many number of slope deflection equations can be written here? We can write for MAB, MBA and MBC and MCB. So here we are going to apply some boundary conditions with the available knowledge of the problem. That is, the moment at this point equal to 0, it is already known, and the moment at this point equal to 0, it is already known. So we can write MAB equal to 0 directly and MCB equal to 0 directly, and the next step is to form the joint equilibrium equation, which is MBA plus BC. That is the moment from B to A direction and the moment from B to C direction. If it is summed up, then final moment should be equal to 0 because it is a simply supported beam. Some residual moment will be created from this direction and some residual moment is created in this opposite direction. If it is minus 10, then this moment will come as a plus 10. So if you sum up these two values, then finally it becomes 0. So that is the joint equilibrium condition. Actually, I recall the steps from first. First of all, you are given with the beam and you make each span as a fixed support, and with the available loading, you calculate the fixed end moment with the available formulas. Next, you write each and every slope deflection equation for each end from A to B and B to A, from B to C and C to B. Next, you formulate joint equilibrium equation with the inner joints. If it is furthermore, it is another span of C to B. If it is another span of C to B, you can form another equilibrium equation as MCB plus MCD equal to 0. We can write continuously if the span extends further. Here only two span considered, then only one joint equilibrium equation can be formed, that is MBA plus MBC equal to 0. So you use this equation as one of the boundary condition. In general, we can clear with the boundary condition. First boundary condition is MAB equal to 0 because the moment at a simply supported point is 0. Then the last end MCB equal to 0. So these are available boundary conditions, and you make additional boundary condition, that is the joint equilibrium condition MBA plus MBC equal to 0. Using these three equations, you can able to find out the unknowns theta A, theta C and theta B. So why it is theta A, theta B, theta C? Because we have the beam profile. We have the beam profile of two span. We have the beam profile of two spans. So what are the points where the rotation is available? So I am making the continuous beam. Basically, you analyze the performance or the characteristics of the given beam. Where will be the rotation available and where will be the rotation is 0. Where will be the moment will available, where will be the moment is 0. Here the rotation, if it is acted upon a loading, so the general profile is like this. General deflection profile is like this. Here the theta will be available, here available, here also available, here also available. And the deflection is 0 at this point. The deflection, the summation of deflection is 0 at this point, and summation of deflection 0 at this point. So you should make clear point from. So for a given beam, you have to discretize the beam with the theta, deflection and the moments. Then finally you form all these equations and you solve with this available boundary conditions, and you calculate theta A, theta B, theta Z, and then you again substitute the theta A, theta B values to calculate MAB, MBA and all other moments. Here if you substitute theta A, theta B value in this equation with the M bar AB fixed and moment, MAB should be equal to 0, because A point is a simply supported point. Similarly for MCB, if you write MCB equation, how we can write MCB equation? MCB equal to MCB bar plus 2EI by L and 2 theta C plus theta B minus 3 del by L. So this is how we can write this equation. So the final moment, if you substitute theta C and theta B, MCB should be equal to 0. MCB should be equal to 0 because we already know it is a simply supported beam. Then you can calculate the value of MBA and MBC using this equilibrium equation. And also if you sum up the value of MBA, MBC, that is also should become 0, because our equilibrium condition MBA, MBC should be equal to 0. We can find some value, MBA equal to minus 30, so that MBC equal to plus 30, you can get any value. But it should become 0 when it is summed up. So next, how we can able to draw the bending moment and shear force diagram, you can see. So in this up to this slide, I think we are familiar with the procedure of the slope deflection equation.